Okay, this is lesson 9.4, intersection of three planes. So I've done my best here to represent what this might look like. The first case is when you have three planes, all kind of go in different directions, and they intersect at a point. A good way to think of this is looking at the corner of a room or a roof, a rectangular room. So if you look at the roof right here, in the top corner by that Batman symbol, that corner of the roof would be like three planes intersecting each other. Okay, so that's one way to look at it. Case number 2 is where the three planes all intersect on the same line, almost like the spine of a book. So if you have a book, several pages, they're all essentially intersecting on that one spot at the spine of the book. Okay. Case number 3 is when two of the planes are coincident planes, and they again intersect at a line, but the only difference is two of the planes are the same, so we're only looking at one line again. And finally, the fourth case is when they're all coincident planes, so they have infinite number of solutions. So your options for solutions here are a little different. You have the option for a point, option for a line, and then infinite number of lines. These are consistent systems. We're going to learn about inconsistent systems after, and I'll show you what those look a little later. So what we're going to do is actually show you a consistent system that's coincident. So think of it like this if it was written algebraically. This would be coincident system. So coincident system. They've given us these planes. We'll call them plane 1, which is x minus y plus z is equal to 1. Plane 2, 2x minus 2y plus 2z equals 2. And plane 3, 8x minus 8y plus 8z equals 8. Okay? Clearly just made them up. But these are all scalar multiples of each other. I can take the first one and multiply it by the number 2 and get the second plane. I could also take the first plane and multiply it by a scalar of 8 and get the third plane. And I can do the same with from plane 2 to 3. I can multiply that by 4. So these are all scalar multiples of each other. Clearly all the same system. Always look for this first. That way you do a lot less work when going through this. Take a look. Figure out if you can find scalar multiples of each other when going through it. Okay? Now in your book, we're actually going to jump to example 3 and then go back to 2 and 1. I think it'll be a little bit of a better order for us. So example 3 is now another consistent system. But in this one, they've given us these equations. 2x plus y plus z equals 1. So that would be our first equation of a plane. Our second equation of a plane is 4x minus y minus z equals 5. And finally, equation 3, 8x minus 2y minus 2z equals 10. Now remember what I told you, let's see if we can find them to be scalar multiples of each other. Can I take the first equation and multiply some scalar multiple to get the second? Anyone know? No, I can't. Right? To get from 2 to 4, I multiply by 2, and that clearly doesn't work for the y. So right away, that's not a scalar multiple of it. Can I do it from 1 to 3? Again, no. Neither work. Okay? So we know that the first one's not a scalar multiple of any of the others, which is good. That means we are going to get something out of this. We also need to check, though, our from 2 to 3. Is 2 a scalar multiple of 3? Yes, this one is a scalar multiple of the other. I multiply by 2. So what we're looking at, when we jump back to our cases here, is we're looking at 2 of them being scalar multiples, in other words, being coincident planes, and one of them not being. We're talking about the third case now. Okay? So, we're going to find a line when going through this question, but because one's a scalar multiple of the other, we can use the three We're going to use our 3 equations to kind of go through it, but we could technically use just 2 equations to solve for this line, just like we did in the previous ones, because really we are looking at just 2 planes intersecting, forming a line. So what we're going to do is I'm going to focus on equation 2 and equation 3. And we're going to work with those. Now we know we're going to get a line, so one of these is going to have to end up being a parameter, but we still do need to make another equation out of it. So we're going to jump back to this. So, in order to eliminate, I'm going to multiply the first equation by -2. So equation 1 will now become -4x minus 2y minus 2z is equal to -2. And equation 2 will keep the same, 4x minus y minus z equals 5. We eliminate the 0, we get 0x minus 3y minus 3z is equal to 3. Okay. When we do that, our equation 4, we'll call it, because technically we already have an equation 3, is -3y minus 3z equals 3. Well, we know we're finding a line, right? So I'm going to have to find a parameter, so I'm going to set one of the parameters right off the bat, z equal to s, we'll call it. Okay? So we've already found the parametric form of z. We're then going to plug that into equation 4 to figure out what our y parameter is. -3y minus 3s equals 3. Clearly I can divide this entire equation by 3. We'll kind of do that at the end when we go through it. But this will then give us -3y is equal to 3s plus 3. And when I divide by -3, y becomes -s minus 1. So there's our second parameter. Our first parameter being z equals s. Second parameter being y equals s minus 1. We then go back to the very first equation that they gave us, x minus y plus z, 2x plus y plus z equals 1. 2x plus y plus z equals 1. And we're going to plug these values in. So 2x plus y, which is -s minus 1, plus z, which is s, equals 1. So I can now find x as a function of s here. 2x minus s minus 1 plus s equals 1. Whoa, I wrote too many s's there. That's a -1. When that 1 goes to the other side, it becomes 2. The s's cancel out. We have 2x. X is equal to 1 in this case. Right? Yeah, it is. So our third parameter for this question, x equals 1. So we have our parametric form of the line where all 3 planes are going to meet. If we go to put it into vector form, okay, our parameter is going to be, or our line is, our vector r is equal to, we know it's going to be r naught plus, and we'll use the s here, and our a value. So for x, a1 is 0, y is -1, direction vector, and z it's 1. So we have our direction vector m here, or a, as I usually call it. And our coordinate x is value of 1, y is -1, and z is 0. So there is the equation of our line in vector form, and the other ones represent our parametric form. And that's where all 3 of the planes cross each other. The only thing is 2 of them are coincident planes.